Let's discuss AC voltage controllers, which are basically AC to AC voltage controllers. Um, Many of these circuits convert one AC signal at one frequency to another AC signal at another frequency. Some of the circuits also change the RMS value of the circuit. That is, they change the shape of the output waveform as well. So, um, and some circuit only change the RMS value. They don't change the frequency of the circuit. So we'll discuss all different types of circuits under AC voltage controllers. So we're gonna start with on-off control circuits and phase angle control circuit. Now all the AC controllers, they use thyristors to control the AC signal, that is to convert the power from one frequency or one level to the other frequency or other level. And all these thyristors that are used, of course, since AC signals are positive and negative, so all these thyristors are naturally commutated or line commutated. That is, when the current, when the signal is going towards the negative side, negative direction, and current falls below the holding current, then thyristors stop conducting. So thyristors, of course, as we have discussed, you can trigger them anytime to start conducting, but to stop conducting, we need to have the current that is passing through the thyristor goes below the holding current. Okay, so let's look at on-off control circuit. Look at the circuit, it's extremely simple. You have two thyristors, one connected, and call it forward bias, one is connected, call it reverse bias, and both are connected parallel to each other. So in the positive cycle, T1 you can trigger and it will become on, and in the negative cycle, T2, when you trigger it, it is going to become it's gonna turn on. And of course the output voltage is going to be equal to input voltage when the thyristor will start conducting in the positive cycle T1 and in the negative cycle T2. So on-off control circuits, basically what we do is we turn thyristor T1 and T2 on. Of course only one thyristor will be on at one time in the positive cycle T1 and negative cycle T2, but we go for n number of cycles. As you can see here, we go for n number of cycles, and we turn the thyristors on at a specific angle, firing angle, right? And then we go for m number of cycles when both the thyristors are off, so we don't send a signal to their gate, and the output looks like this. So when it is on, let's assume that we are turning them on as soon as the cycle is coming. That is, our firing angle is 0 degrees for positive side and 180 degrees for negative side, right? Or time, if you think in times, is 0 for the positive, and t naught by not t naught by 2, but whatever time is t by 2, whatever time is that. T naught, of course, refer to the output time period, which will be different than the time period of your waveform. So whatever t by 2 is here, that's going to be when we send a signal to the gate of thyristor 2. So as you can see, the output is in 2 cycles. So we are turning it on, T1 on and T2 on for 2 cycles consecutively. So the output is sinusoidal waveform, and then we are not turning them on for 1 complete cycle. So we creates a gap, and we did not turn it on for 1 cycle. So there is nothing at the output, and then the pattern will keep on going. So you have 2 cycles when it is on, 1 cycle when it is not, they are not on, and the output will look like this. Some of the applications are here: industrial heating, speed control of motors, and stuff like that. And output RMS value, of course I have derived all these, so make sure, I will highly advise you, don't just read it, do it yourself. Do it on a paper with a pen, so you understand them properly, you know how to do the math, and if I ask you in the exam, you don't have to go and search for it, in books and stuff, and waste time. You should be able to do it. And even if I change anything, as long as you know how to do it, you should be able to do it. So go over this. I'm not going to go over each step, but for n cycles that it is on, of course, is going to be from 0 to nt. T is the input time period. So for that much time it is on, and the total time period of the output is m plus nt. So this is the total time period up to here, which is n cycles plus m cycles, and then the time period of one cycle is uppercase T. So go over this and you will see that the RMS value, it is the source RMS value divided multiplied by square root of n over m plus n. Okay, and we call duty cycle n over n plus n. That's what we call duty cycle. So output RMS value is square root of duty cycle times RMS value of the input voltage. Go over the problem. Okay, next circuit is principle of phase control, or the phase control circuits. As you can see, there's one thyristor and then one diode. So in the positive direction, you can control when the output will be transferred, when the input will be transferred to the output, but in the negative cycle you don't have any control. It will be on for the whole negative cycle. Okay, so you can see that we have the delay angle alpha or firing angle alpha. So positive cycle, whatever firing angle it is going to be, positive cycle is going to start from there, and of course the whole negative cycle is going to be conducted through the output. So that's going to be the output. It's also called unidirectional converter, of course, since only one direction can be controlled. Again, look at the RMS value and do the derivation. Average a problem. Then you have a bidirectional control, similar circuit as you saw in the first one, on-off control, right? Exactly the same circuit. The only difference is going to be that we are not keeping the thyristors on consecutively for n number of cycles and then turn them off for m number of cycles. Rather, we will be firing them in each cycle. Okay, so we are firing them at an angle alpha right here, and then firing the negative cycle the same angle but after 180 degrees or pi. So pi plus alpha right here. So this is the output. Okay. Average value, as you can see, is 0 because you have the same area in the positive cycle and negative cycle, which will cancel out. So average value is 0, and RMS value is derived here. So do the derivation of RMS value again. Make sure, do not just read it, do the derivation. And the last type of circuits are called cyclo converters. Basically, AC frequency changers. They change the AC frequency as well as, of course, the RMS value of the AC signal as well. Actually, they just looks like they just change the frequency, not the RMS value, because you have equal number of cycles. Well, they do change the RMS value, of course, because the output doesn't look like the input, and they also change the frequency. And the frequency is a fraction of the input frequency. So there's a specific number of the output frequency that you can select. Let's say, for example, if input frequency is 60 Hertz, then you can only do a fraction of that. Let's say half. So the output can be 30 Hertz, 1/4. Then output can be 60 over 4 Hertz, 15 Hertz, and so on and so forth. But output has to be a fraction of the input frequency. Okay. This is how single phase cycloconverters look like. So you have, there are two bridges. This is the positive bridge, which is also called P converter, and this is the negative bridge, which is called N converter, and load is in the middle. So T1 and T2 in the positive converter are fired simultaneously. Likewise, T3 and T4 are fired simultaneously. And in the negative converter, again, T1 dash and T2 dash fired simultaneously, and T3 dash and T4 dash are fired simultaneously. So based on how much frequency you need at the output, let's say you need 1/2 of the input frequency. So for one half of the input frequency, your time period is going to be double the amount of the time period of the input. So if your input time period is 1 millisecond, the output time period has to be 2 milliseconds, right? Okay, so let's look at how it is going to work. Okay. All right. So first, T1 and T2 is fired. Okay. Now let me go over there. First, T1 and T2 is fired. So the current is going to flow from Vs T1 load from top to bottom, load T2 and back to the other side of Vs. Then that is during the positive cycle, T1 and T2 is fired, right? Now the first negative cycle, T3 and T4 are fired. So current is going to go from the negative side of Vs, T3 load in the same direction, right? So that means the output voltage will be in the same direction from top to bottom, positive, negative. Go back T4 and go back to the top side of Vs. So that's only positive cycle, right? So the positive cycle appeared as the positive at the output, and the negative cycle of the first negative of the first cycle also appeared positive at the output, right? Let's go to this waveform. So positive cycle when it is fired is here, and the negative cycle when it is fired, it flipped over because the current was flowing from top to bottom, right? Okay, so both cycles become, well, the first cycle was positive, but the negative cycle become positive as well. Okay, now for the second input cycle, we went ahead and we fired T1 dash and T2 dash. Okay, so current is going to go here, it's going to take this route right here, T2 dash through load. Now it is going through load from bottom to top. That means the voltage induced is going to be in the opposite direction, bottom to top. Then T1, it is on, or it is conducting, right? And then go to this node, go back and to the negative Vs. So the positive cycle of the input becomes negative at the output when T1 and T2 were fired, T1 dash and T2 dash were fired, right? Okay, now we go ahead and fire T3 dash and T4 dash when the negative input cycle come for the second cycle, negative part come for the second cycle. So we take the bottom one, go from here, go to B, go through T4 dash, go through the load, again going from bottom to top. That is, the voltage is in the negative side with respect to the polarity that is shown. And then go, T3 is on, so go through T3 dash, go back, let's go back here and on the positive side. So for the second input cycle, both positive and negative, they produced negative at the output, right? So what happened now? The output time period becomes double the input time period, and the frequency became half. So the frequency, if the input frequency was 60 Hertz, frequency became 30 Hertz, output time period became double the input of the input time period. So 16.667 input time period, the output time period became, 33.2 or something milliseconds. And this will keep on going, right? So important thing is that you understand the sequence in which thyristors are going to be fired to produce a specific output for a specific frequency. Okay, it is important. I will advise you to do some exercise. I'm not assigning any homework, but do some exercise. Let's assume that if you want the output frequency to be 1/3 of the input, like so whatever, if it is 60 Hertz, you want the output frequency to be 1/3 of that 20 Hertz, and see how it's going to work out at the output, right? See which will be fired and how the output is going to look like. It is a good question. It is an important question. So do that. This one is 30 hertz, half of it. Look at the derivation of RMS voltage, output RMS current of each thyristor, and so on. So all these derivations are given to you. Make sure you look at them. I'm not very interested in since all the derivations are given to you. I'm not going to give you exactly the same thing that you can just look at it and then put down the answer. So I'm more interested in that you understand how the circuit is working, and if I ask you to explain or ask you what's going to happen if you do this and this, then you know how this circuit is going to work. So do that, and then this is the end of all the topics that we had to discuss in power electronics for this semester.